Hello, it's Legs again, back with you in our Rankings Explainer series. And let's talk about the rankings algorithm itself. It involves some tasty equations, and if you're one of those people already feeling your mind clouding over and your limbs shaking at the thought of all that math that is coming up really soon, just stop, be present, inhale, exhale. The algorithm is really not all that bad. We're just going to hold our breath past a few logarithms and it will all make sense. I promise. Just stick with me. And what's most important here anyway is how you can put it to use for your team. We let computers do all the hard calculations anyway. Okay, so what exactly are rankings again? Ratio-based rankings do two things at the same time. Number one, they give a number of ranking points for each team that indicates their strength based on the games they've played so far. And number two, they predict the outcome of future games based on the ratio of the ranking points between teams. And when we say algorithm, we're really talking about that first part. In other words, we're looking for rankings that explain as closely as possible the actual outcomes of previous games. If Team A scored this and Team B scored that, then the ranking must be X or Y. And we do this in such a way that the second part, predicting future game outcomes, happens automatically. Now, no algorithm can do this perfectly for more than a few games because sports, humans, the weather, luck, the wheels you got against the floor, and different strategy matchups between teams and everything that makes roller derby so awesome all introduce different variations into scores that no rankings could ever get perfectly right. The trick is just to get as close as we can. Unless you're Champoury, and in that case, you are perfect just the way you are. We chose to use a linear regression method, weighted least squares, which is popular in statistics and data analysis. And we found it produces the most accurate rankings. And see our later video for exactly how we measure algorithms to see how accurate they are, to prove this to ourselves that this was a good choice. The term linear regression sounds very fancy and evocative, but don't get too excited. Originally, regression actually just described a tendency towards mediocrity, or the average, in inherited biological traits like having tall parents and then how that tended to average out in descendants. And the linear part just refers to finding a line to match a given data set. That's basically linear regression, a straight line that matches the average slope of data. Least squares is also a fancy sounding term, but it just means you check how far off your line was from each real data point, and then square the error value. Squaring, by the way, in math is often used to get rid of negatives, and it also boosts the signal a little bit. So the best fit line will be the one where the sum of those squared error values is the leastest, or the smallest. That's why we say least squares. And weighting just means some of those terms will get a different weight. For example, if a game is a blowout, we will count it for less. So all this means is we have an equation that makes a best fit line through all the games. In other words, the line with the least error. And some of those errors will be weighted differently. That's all weighted least squares linear regression really means. We go deeper into this a little bit more and how to visualize it step by step in a future video or two. But to work with the algorithm, all you need to know is game scores are data points. We want to explain those game scores by giving each team the best ranking possible. And the mathematical way we do this is by finding a straight line that passes closest to all those data points. In order to find that best line, the algorithm needs to know all the data points it needs to account for. That is why we use all the game each team has played so far this season. It's like that weather analogy where we said we needed to know the weather on the coast to understand the weather inland. We will talk more about why we need to look at all the teams and all the games later on in the video, all the games all at once. But what's important here is we need all the games for all the teams for the whole season, and everybody's ranking and the outcome of every game affects the rankings of everyone else. Okay, that's it for the base concepts. Let's dig right into the equations. You ready for this? Here's the equation at the heart of the algorithm, and do not be intimidated. We are going to break this down right here, right now. We're going to talk about that W term, the weight term, in the next video, so we're just going to take it away for now. And that little squiggly W is the lowercase Greek letter omega, by the way, in case you ever wondered what omega looks like. But it sort of looks like a W, so we use it for weight. Let's take that away for now. That squiggly E, epsilon, at the end is for error. It represents the error between the best fit line and all of our game scores. That's that thing we're trying to least squarify or minimize. So less errors, more better. And see all those LNs? That stands for natural log. Don't let them scare you. Taking the log like this simplifies the rest of the setup a lot. We have a whole video on what logarithms are and why they are so damn cool and why we use them in the algorithm, and I'm so excited to do it, and it's way too long and super duper interesting with a ruler and pictures and everything, but it's way too long, so it's going to be in a different video. But here's a quick rundown to give you a heads up. Our rankings are ratio-based, which means we are always talking about the ratio of ranking points between teams and the game score ratio, so taking one thing and dividing it by another. Lots of division happening everywhere. And division and multiplication tend to create graphs that look like this. Notice anything? Well, don't think too hard about it. The thing about these graphs is they are not straight lines. But we're using linear regression, right? Linear, straight line, and these curves are all curvy. So how do we straighten out all those curves? It turns out, if you take the log of score ratios and ranking points ratios, it magically transports us into this mathematical land where all those curvies turn into nice straight lines. And then we can use linear algebra. So do check out the logarithm video for more. It will explain it all. But this is why the logs are in there. Okay, so let's take a step back. We are trying to find ranking points ratios between teams. And we want that ratio to explain the score ratio of actual games that were played. And that squiggly equal sign just there just means equalish. So we're looking for a game score ratio that is mostly equal to the generated ranking points. And we take the log of both sides to make things linear. And one really cool thing about logs is that if you have a log of a ratio, it is the same thing as the difference between the log of the top and the log of the bottom terms. So the log of the ranking points ratio between two teams is the log of the first team's ranking points minus the log of the second team's ranking points. So we could say the log of the score ratio is equalish to the log of the first team's ranking points minus the log of the second team's ranking points. We can remove that one division and just keep the subtraction in there to make things easier. And we can make things look even nicer and just say S equals the log of the score ratio and R can mean the log of the ranking points for each team. And we're just sort of hiding those logs away for a while. We're going to remember they're there, but we'll take them out of the equation just to simplify how things look. And this is looking like a regular old linear equation with just minuses and pluses in there. And how do we get rid of that squiggly old equal sign? Well, all we do is admit that our ranking points are not going to be able to perfectly explain every single game score ratio. So we add in that fancy E for error, and that's just the error between our best fit rankings and the real score ratio. And now we have a real normal equal sign. And this is the form of the equation we need to use least squares regression. And it's more than enough for understanding the algorithm. So if you've got up to here, you're good to go. But what if we want to understand how to start from the actual game scores and set this up like you were writing the computer code to do in algorithms? So we're going to take this nice, simple, beautiful equation here, and we're going to set it aside for a moment and see if we can recreate it using actual game data coming at it from a different angle. So remember, for every single game in the season, we need to take into account every single team's ranking points. This is because all teams are connected and the linear regression algorithms need us to take every single team into account. Remember the weather analogy? So let's say we have 100 teams. For every single game between only 2 of them, we still need to determine our linear equation for every single team. So 100 teams means 100 terms plus the error term. So you could read this long equation something like, the log of the score ratio is the contribution of team 1 times the score ratio of team 1 plus the contribution of team 2 times the score ratio of team 2 plus the contribution of team 3, blah, 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 up to team 100, and then the error term on the end. Holy moly, that is a lot of terms just for one little game. And we would need to do it for every single game in the season, which is thousands, right? Yuck. Well, luckily, I slipped a new little element in there, secretly, that makes things easier. What the heck do I mean when I say contribution? Well, for the algorithm to do its magic, we need terms in the linear equation for every team. However, for an individual game, we only need to worry about the ranking points for the two teams that are actually playing the game. So we do a little tiny trick here. Of those 100 terms, for the 98 teams that don't play in the game, we set the x term to 0. For the team on the top of the score ratio, we set the x term to +1, and the team on the bottom of the score ratio equation, we set the x term to -1. Why do we do that? Well, all those zeros go away, and so for each game, we get something like this. Look familiar? Well, it's a lot simpler, and it's also our equation from before. So if you have a bunch of teams that have played a bunch of games, what you do is create a system of linear equations, one for every game in the whole season, and every single term, or every single team has a term in that equation. Then we set the x value for each team to 1 if it's team 1 in the equation, -1 if it's team 2 in the equation, and 0 if the team doesn't play in the game. And we will include all the virtual games in this too, by the way. Once you have that all set up, you can spend a really long time with a calculator and a notepad, or you can just stick it in some computer code and use an existing statistics library like we're using here, stats model in the Python library. And with that one little line in the pink box, all of your team rankings pop out. So you put all the games for all the teams in here, and in that one line, takes a few seconds, and then out pops all the rankings for all the teams. Pretty cool, huh? And not that much work, really. You don't need the notebook and pen. You can do it with a computer. And remember, so we're solving for those R's, right? The team rankings. But they're not exactly the ranking points for each team. They are the log of the ranking points for each team. Remember when we simplified the equation earlier on. So to get back to the rankings points for publication or to use in ratios and game score predictions, we have to take the inverse log. This is done by taking the number e and raising it to the power of the r that we got. We use e, known as Euler's number, because we use the natural log, ln, when calculating our logs. And that ln just means log base e. That's versus something like log base 10, which we use for pH, or decibels, which you might be familiar with. The algorithm totally works with other log bases as well, but you have to be consistent that you keep the same log base all the way along. And by the way, Euler's number and the natural log are pretty darn cool. They crop up all the time in nature, like anything that springs or wiggles or shakes or makes babies. And it's super interesting. I'd love to talk about it, but it's a topic for another day. That is why it's called the natural log, because it's kind of natural and shows up in nature. But super cool. And we have a hockey joke about Wayne Gretzky here, told by the hippo. And if you don't get it, do some research on Wikipedia. And, well, that's really it. That's the algorithm. We take the log of the game score ratios. We set up the terms of the linear equations just right, one for each team, one for each game. We feed it into a linear regression stats library, and by the power of math, the log of the best fit rankings pops out. If you want to see some examples of what setting this up looks like exactly in practice, and a Python code snippet of how to code this and how we call the stats library, check out the more detailed algorithm explainer doc. And if you want to dig a bit more into weighted least squares for sports, read this 1997 paper by Massey, who side note, blessed our algorithm system for roller derby, so that's really cool. And check out the great work of Sam Skipsey, who implemented this for roller derby in the past, notably for the World Cup. There's one more term to talk about to fully understand the algorithm, which is the weight term. So we will cover that in the next video. Thanks a lot for your time. I hope that helped break down all the scary math, and you are very excited to get using this new algorithm.